In this video, we're going to take a look at some special exponential derivatives and how to take them. We're going to use a technique called logarithmic differentiation. And before we start, I'm just going to give a quick explanation as to what this means. It means using a log or an ln to extract a variable from an exponent. So we have something like, if we have something like y equals 3 to the x, we don't necessarily have an easy way to derive that. Now, you may know the formula for it, but we're actually going to go through how to do it here. Let's say we want to take the derivative of this. Well, we can't use the power rule because if I were to use the power rule, I'd actually be altering a variable rather than a constant. It's not the same as x to the third. So instead, what we're going to do is I'm actually going to get this x out. And to do that, I'm going to take the natural log of both sides. What this allows us to do is, if we remember, the log of a to the b is the same thing as b log of a. It's one of our log laws. So I can now rewrite this as ln of y is x ln of 3. Now, I can take the implicit differentiation of both of these sides here, 1 over y dy dx. And now, note that ln of 3 is just a constant. So if this were like 3x, the derivative would just be, well, 3. So in this case, the derivative is just ln of 3. Now, we're just going to bring this down here because I ran out of room. Now we're going to multiply both sides by y to get dy dx by itself. So now my dy dx is y times ln of 3. And y, from the very beginning of this problem, is 3 to the x. So now I can substitute that in, and we get 3 to the x ln of 3. Now again, you may remember the equation that if we have y is equivalent to a to the x, then the derivative of it is a to the x ln of a. Well, that's how we get this. If I were to perform these steps with any number other than 3, it would work exactly the same way. So now that we have some background, let's check out a couple of really cool derivatives here. The first is y equals x to the x. And that's somewhat of an interesting function. It rises exponentially really quickly if we were to do some numbers on that or graph it. But here I'm just interested in taking the derivative. So again, I can't use the power rule because we have a variable in the exponent rather than a constant. So I'm going to go ahead and take the ln of both sides to get that variable out of the exponent. And then bring that x down using our log laws. Now, take the derivative of both sides. So again, this is 1 over y dy dx. This time we don't have a constant as ln of x, so we have to use the product rule. So it's the first, which is x, times the derivative of the second, which is ln of x. And if we forgot the product rule, it's first times the derivative of the second plus the second times the derivative of the first. So this is the first, and derivative of the second plus the second times the derivative of the first, which is just 1. And just like in our previous example, I'm now going to multiply both sides by y to get the, to get the dy dx by itself. So multiply both sides by y, get rid of that, and we're left with dy dx is x times 1 over x is just 1, plus just ln of x times y, and again, y is x to the x. So just like here, I substituted in the 3 to the x. I'm going to substitute in x to the x. So my final answer is going to be, when distributed, x to the x plus x to the x ln of x. All right, so let's try a slightly tougher one here. Same principle. Okay, again, I have a variable in the exponent, so we're going to use logarithmic differentiation to get that out. And again, we're going to bring that down using the log laws. Right. So now, take the derivative, 1 over y dy dx. And again, we have a product rule here. So this is the first. And this is the second, which will require a chain rule as well. So it's the first times the derivative of the second, which is 1 over sine of x, but don't forget to multiply that by the derivative of the sine of x, which is cosine of x. Okay, because remember, this itself will require a chain rule. Plus the second, which is ln of sine of x, times the derivative of the first. And the first is just x, so the derivative of that is just 1. So let's simplify this. We have 1 over y dy dx is x cosine of x over sine of x plus ln of sine of x. And we can go one step further here and say 1 over y dy dx is x cotangent of x plus ln of sine of x. Now, same process as before. Multiply by y, multiply this side by y as well, and again, y is sine of x to the x. So my final answer here is going to be dy dx is x cotangent of x sine of x to the x plus sine of x to the x ln of sine of x. It's a mess, but that is the correct answer for the derivative of sine of x all to the x. I hope you found this helpful. If you'd like to see some more videos, subscribe to our channel, and feel free to email us as well with any questions you'd like answered in video form.